which were used to sequence the Human Genome Project. And then in 2016, it's been replaced by all these high-speed instruments, and now you have the extended linear sequences. And the way they actually interpret the sequences is slightly different from what we used to do there. It's massively parallel short read sequencing, also shotgun sequencing, which is great. I wouldn't call it next generation now because it's been there since 2008. Probably better to call it high throughput sequencing. So this is just actually the way it looks. So these, how many of you have actually done Sanger dideoxy sequencing? Okay, so basically the technique is you take the DNA from a genome, break it down or different short fragments. You can either clone it or just do a PCR amplification and then run it on the sequencer using sequencing primers. And what you get is a readout of ACTGs because each of the dideoxy has a different color code. And when it stops, so the shorter the fragment is the first closest to the starting position, the longer fragment is close to the end, and then you just read it from the 5' to the 3' direction there. So the next generation sequence is slightly different because what you get is reads from the same position, but then you just pile them up on top of each other. So whereas a mutation in the old one over here, the reference is, so this is in the middle is the reference sequence. It's the same except for this position over here, which is an A in the reference, but it's a C because it's a blue peak over here, it's a C over here. Whereas in the new sequencing, it's basically all these gray bars over here are the same as the reference sequence. Wherever they differ, it shows you a variant, which is a C in this case. And since all of those reads support this C, then it's basically a statistical interpretation that it's a C at that position. Just brief history of sequencing genomes. So it started right from 95, and actually the first human genome the draft was published in 2001. But actually the much better finished version of the sequence was in 2004, and it's been constantly refined since then. So it took us 10 years to do the first sequencing using bacterial artificial clones. This is basically taking the DNA fragments from a bunch of mostly European background individuals and cloning them into these bacterial artificial chromosomes, and then amplifying those in bacterial culture, then isolating selected pieces and sequencing them on these Sanger sequencing machines. But what's really good is that this reference sequence is really good because it has less than one error per 40,000 bases. What happened since the genome was published in 2004 was that around 2006 and 2007, there's a new technology known as Alexa was developed at the University of Cambridge, close to Sanger, and then basically it got bought by this American company known as Illumina, and the cost of sequencing started dropping dramatically, actually even more dramatically than the cost of computing. And so at the moment where we are in 2016, we can sequence one human genome in roughly around $1,000, and whereas it took us 10 years to do the first sequence, today it takes us 3 days to do one high coverage human genome sequencing. Of course, the analysis takes much more longer. And that's just describing the time and the money that was spent sequencing the first human genomes. And then, of course, one of the first machines to sequence the next generation machines was the one which the Roche developed to do further sequencing of Watson's genome. Craig Venter did his own using ABI sequencing as well. But then, since 2010, there have been thousands of human genomes, and just last year we published 2,500. Actually, early this year we published 2,500 human genomes, which were in the 1,000 Genomes Project. So the 1,000 Genomes Project is basically a collection of 100 to 150 samples from different populations across the world, actually 26 worldwide populations covering the main continents, which is Africa, Asia, Europe, and America. It includes also one Pakistani population, which is Punjabis from Lahore. So it's a good reference source for that population. And the aim of that was to characterize all common mutation more than 1% frequency in the population. It was the first project to look at different sequencing platforms. We used at Solid, Roche, and Illumina, and then finally decided in the third phase and final phase of the project only to use Illumina because the error rates for the other machines were pretty high and the results were not very reliable. And also they were, especially for Roche, although it was very reliable, the reagent costs were very, very high, so it was not very practical to sequence thousands of genomes using that. So the first machine was this 454 sequencing by Roche. This has been discontinued now just for the fact that nobody was buying these machines because the reagents cost was so high. The second one to come out in 2006 was the Solexa, which was now known as the Illumina. They have a whole range of machines which I've talked about in why. Solid, which was actually developed by ABI, which had controlled the market for dideoxy sequencing, actually bought both the ion torrent and the solid instrument. They've discontinued the solid because they just could not expand the size of the fragments to more than the sequence fragments to more than 25 base pairs, and that was just not giving very reliable results. The ion torrent is basically, I think you can use it for short, small, targeted projects, and that's what the market is for that. But it also has, you have to be aware it has a 5% error rate there as well. For historical purposes, there was this instrument which was based on single read sequencing. The Hankos, which was basically discontinued because this error rate was more than 10% and was nobody really relied on any of the sequences coming out there. PacBio was interesting because this was the only system which had very long reads. So by long reads, I mean about 15 to 20 kb long reads, and so they could actually be used for de novo genome assembly because the longer the read you have, the more you can overlap those reads and make a scaffold and do a de novo genome assembly. But combining PacBio with Illumina sequencing, you can get a very high coverage and low error rate de novo genome assembly, which is the way people are doing now. The only problem is this instrument is very bulky and it's very expensive, so only a few genome centers in the world can afford to buy this instrument and run it. So starting from the reference human sequencing based on capillary dideoxy sequencing in 2001, this was just the reagent cost. It must have cost the number of man hours and the lab hours working on it is much, much higher. Then you get, I think the next one was also Craig Venter. His sequence was also available through dideoxy sequencing. And one of the first next generation was Jim Watson, the guy who actually discovered with transcript the structure of DNA. He sequenced his own genome in 2008, and that's also available publicly. The Illumina started by sequencing the acute myeloid leukemia patient, also used by some Chinese genome, and then they did some African genomes and some trios. And so basically Illumina sort of established itself as one of the players in this next-gen sequencing market. Stephen Drake did, I think he's at Harvard right now, he did it through Helipos, but it's basically an obsolete instrument now. Complete Genomics came up with a new plan that they don't offer any instrument, but they offer a service. So you can send your DNA samples to them and they can sequence it for you on their machines, which are based in California. But they got bought by BGI recently, but they still haven't offered any instrument, but they do offer this service. And their aim is more towards the clinical market. And we actually had a project in which we had sequenced genomes. I probably talk about it when I'm giving my population evolution genetics lecture. And the results are actually quite good for complete genomics. But so, I mean, that's another option that you can outsource your DNA sequencing, which is probably the best way to go in Pakistan. So this was back in 2009, and this is actually the current. It's basically, I think, most genomic centers I know of are basically working on Illumina platforms, and they have a number of machines. They have a MiniSeq, they have a MySeq, NextSeq, HiSeq, and HiSeq 10. That's for low throughput projects, for very high throughput. Initially, it was only for human genome sequencing, but now it's been approved for sequencing any genomes using the HiSeq 10. But you need to remember that you need a really big sequencing center with a lot of place for data storage to have one of these instruments. Otherwise, there's no point in getting one of these. Thermo Fisher Scientific bought over the ion proton and the ion torrent manufacturers, and they discontinued the solid because it wasn't really a market they were looking into. Complete Genomics has no instrument to offer. PacBio has Sanger has this PacBio RS2, which is the older system, but the new sequel system is supposed to be better and even much smaller than the original one. And the really exciting new player on the market is Nanopore Sequencing, which is a company in Oxford known as Oxford Nanopore Technology. They've already released the MinION and the ProMethION, which is their high throughput, and the one which is actually connected to a laptop and you can sequence it. It's based on nanopores which have a tag DNA polymerase, and when this sample goes through the pore, it gets sequenced and it's detected. This is something which is actually a very small sequencing device which you can attach to your mobile phone, which they're developing for basically the field. So I think this Oxford Nanopore has a lot of potential for the epidemiological and field genomics, genomic diagnosis on the field, and that's the market we're aiming for. Currently at Sanger we have it in research and development, and the error rates we're coming up with are actually quite high for any useful human genetic and clinical purposes, around 5%. So, but we're getting some reads which are as long as 100 kb. And basically you get this, you run it on the instrument and plug it to your laptop, and you start getting the sequences coming out, and next morning you can actually look at your sequences. You just throw the flow cell away and order a new one. It's roughly around $2,000 at the moment, but they project that the price will come down to around $300. The other thing you have to remember with these sequencers is that if you've got long tracts of A, C, T, and Gs, they're not very good at detecting those, and you get lots of errors in those positions. This is an overview of the sequencing centers throughout the world. So Sanger has about 3% of the sequencing capacity. It's actually more now because recently Illumina moved their operation to Sanger as well. And then you've got the Broad Institute, which is our main competitor in the USA. BGI is one of the largest sequencing centers in the world. This is the new sequencing building at Sanger. So the top two floors are Sanger. The bottom floor has been just taken over by Illumina. So Illumina has moved their research sequencing into Sanger. And this is headquarters for Genomics England, which is a big sequencing project in which they're sequencing 100,000 human genomes for the National Health Services in the UK. And because it's patient data, it has to be managed access. And so they set up this whole new sequencing laboratory, and it's just got 6 sets of X10 machines, which is like 60 machines. And it makes it one of the largest sequencing centers in the world. So some of the main projects we are involved with is, how many of you have heard about the Human Genome Diversity Project? So this was a project which was set up in the late 90s by Cavalli Sforza, and Professor Howard Kahn recently died. And it was basically to look at populations which were interested from the anthropological and genetics point of view. And this includes actually 8 populations from Pakistan, which we collected while I was working here. And it's become a reference population for pretty much population genetics. And what we decided in collaboration with the Broad Institute was to sequence all 1,000 of those samples. So the sequencing will be probably completed next month. So by the end of the year, you'll have another 200 high coverage Pakistani genomes to play with. Genomics England is the 10,000 genomes, which includes 50,000 cancer genomes and 50,000 genomes from people with Mendelian and rare disorders. And of course, you've got literally thousands of cancer genomics, which Wesley was talking about, coming through the Cancer Genome Atlas and the Cancer Genome Program, both at the Wellcome Trust and elsewhere. Sanger is also, many people don't know, it's the largest knockout mouse facility in the world. And so the aim was, it was a European Union grant in which they were knocking out each of the roughly 20,000 genes in the mouse, and then looking at phenotypes and seeing what each of those genes was. And we're involved in this indirectly because we're generating mouse models for human alleles that we're interested in modeling. And some of the first models coming out of that look also very promising. And Sanger also sequences pathogens, and it's especially the malaria project at Sanger is one of the biggest in the world. And they're looking at variation in the malaria parasite, both falciparum and virex. And they're also looking at lots of bacterial genomes. This includes cholera, salmonella, and lots of other parasites which are especially in Africa and Southeast Asia. And Sanger sequences roughly around 40 to 50,000 whole bacterial genomes just last year. So they have a number of huge sequencing data sets. And what's becoming clear is that the sequencing data sets are becoming exceedingly large. When we started out, there was a lack of standards. they needed complex computational tool like Wesley was talking about, and they also needed lots of integrative experiments like the ENCODE project started off with. And then of course there's always problem of reproducing this data and accessibility. So very early on Sanger realized that saving the images from those sequences, it was not an option because they were just taking up too much space, and it was actually cheaper to repeat the experiment than to store the data on the computer. And at the moment our major costs are actually not reproducibility but actually storing the data. And currently the Sanger storage has about 25 petabytes, which is one of the largest in life sciences. And they're going to, in the next 2 years, it's going to increase to 80 petabytes, which will probably be one of the largest in the world after CERN for physics databases. So for all next generation sequencing, they're just 4 steps. What you take is take your organism which you're interested in, you fragment the DNA into small pieces, then you sequence those fragments, and the difference in the technology is actually how long those fragments are. So the longer the fragments are, the better your sequence will be, because you can then overlap them and basically form a good scaffold. Most of the techniques which were like the solid had 36 base pair fragments, and they really weren't able to extend that much further. So that's why that technology failed. Complete genomics also had 35 base pair, but then their coverage is quite high, so you can actually for regions of at least for the human genome which map very well to the reference, you can actually do good coverage for that. So that's why I think it sort of survived condemnation for itself. And then of course once you have these fragments, then you map these fragments back to the reference sequence, which for the human is the human reference sequence, which is a really good reference sequence which has 1 in 40,000 bases error. And once you map it, then you look at differences between the reference and your sequence, and that's the way you actually call the DNA variation. And of course, there are clever ways to call the proper number variation and the kinds of variation, which we will probably discuss more in the next few talks.
Dr. Al, can I ask a question about that?
Yeah, sure.
Is it, when you do this sequencing, is this all sort of done automatically, or you have somebody that's working doing?
So we have a core sequencing group at Sanger, and so the people actually do the library preparation. So there's a group which does the library preparation. They hand it over to the other group which loads we basically do the library QC, which is usually done on an IC. And then once it passes the QC, then we basically load it onto the instruments. And then the instruments just run, somebody just has to replenish the buffers and all. And if there's any problem with, Illumina has an engineer on site.
Reconstructing the fragments?
So that's a core bioinformatics group.
Okay.
And what they do is they go through for the 1,000 genomes, the pipeline they set up, that's basically what they're using. They've chosen a reference which now is, I think, the build 38. They map it to that reference and they call the variant using the GATK. And that's pretty much standard across the institute. And like our group, what we'll get is after they map those, we get the DAM files and we get the raw BCF files, and we basically do what we want to do. So, as I mentioned before, the Sanger sequencing is based on dideoxy terminators. The instrument used to cost 100,000. I mean, I think ABI still sells one, and there's always, I think it's still got a market because there's one kind of variation which most of these sequences don't cover very well, and those are the simple tandem repeats which are used for forensic analysis. And so for those, I think the ABI sequences still have a market, and especially for forensic purposes. The Roche titanium was based on this emulsion PCR and polymerase pyrosequencing. The Illumina, I'll talk a bit more detail about this because this is currently what most people are using. I would just ignore ABI solid. It's just there for historical purposes. Iron torrent is more like a glorified pH meter. It also has a lot of errors, so it's good for certain targeted resequencing projects. So if you're interested in a particular gene and you want to sequence, let's say 2,000, 3,000 individuals, so you just do a PCR amplification for that gene and then run it on one of these sequences. This is obsolete as well. I'll also probably add a time we'll show TacBio video for that's interesting as well. And then the complete genomics uses this combinatorial probe ligation analysis, which the paper was published a few years ago. These are the costs over here. They've probably gone down, if anything, over the last 2-3 years. So the Roche actually was a pretty good instrument because it had long base pair reads, and throughput was pretty low. The error rate was also very low, which is really good. It was the dominant errors that you saw in that were basically index, which is single nucleotide deletions in the cells, would really throw the instrument off. And there was very low disconcordance between the genotypes. The Illumina genome analyzers started off with actually even less than 75 base pairs, but currently you can sequence 75 to 300 base pairs depending on which instrument you have. The error rate is remarkably low. The throughput for the latest, the X10 is actually 1.8 terabytes per instrument, so it's huge. They have one particular, the error rate is pretty negligible right now, especially if you cover the same position multiple times. And it's actually less, in most instances, less than 0.1%. Solid is the one which maximum you've got read lengths up to 50 base pair, but their error rates were pretty high, and although they claimed it was less than 1.1%, it was never the case, at least at Stanford when they used it. And that's why the 1,000 genomes, after the pilot phase, decided not to use solid seq.
How can we calculate the error rate in our data, in our own experiment? So we have some data from Illumina,
so
and we can.
What Sanger does when every time they get a new instrument is they have, so there's a YRI trio which has been sequenced on almost all different platforms. So there's a paper that is in bioRxiv, I don't think it's been published, it's called Genome in a Bottle, and they've actually compared those same three individuals, mother, father and child, across all those instruments. And they also have very good Illumina genotypes for those samples. So they look at disconcordance between the sample and sequence and say basically look at the overlap, which are called correctly, which are not called correctly, and then estimate the error rates and false discovery rate based on that. So you need to have, whenever you set up instruments like these, you need to have somebody or a control sample, and the best is to use one of the CEU sample, which is a population sample from Europe. Collected in North America, or to use one of these YRI trios, which are African samples, and to compare how well your instrument's running.
Otherwise, we have to trust the instrument.
I would not trust the instrument like that. You can get really terrible results.
Excuse me?
Yes.
Dominant error type is index or substitution. It is compared to reference genome?
This is compared to the because the ABI sequence human reference genome is a really good standard. So everything we do here was compared to the reference sequence.
Changes
So that's an important question. So when you do look at which reference genome you're comparing to, make sure you're looking at the latest one, because the latest one is the most refined version of the genome. For 1,000 genomes, they used build 37. Now, for the AGDP-Ceph panel that we're sequencing, we're using build 38 because it has a lot more copy number variations in it, which 1,000 genomes identify.
Do they use some specific algorithm for comparison or alignment or?
No, so you use whatever your preference is. There are now a couple of standards for calling the mapping files and also for variant calling, which people usually use and are considered to be reliable. But I think every time you use it for the first time, always compare it with something which is being published and see how your results compare with that. Because if they're really bad and there's no low concordance, I
just want to ask when they compare, they use some specific algorithm for comparison?
So basically, let's say, what is your interest? Human or not human?
I'm basically computer science.
Okay, so let's say you sequenced a human genome, and let's say you've sequenced one which was sequenced by 1,000 genomes. You take that sample and you compare it what the variant calls were with 1,000 genomes. And if the error rate is more than anything more than 1%, I would say that your sequences are not really, or your variant calling is not very good. Because you need to be as good as the one which has been published is.
I just want to ask, there is some algorithms like Middleman-Wunsch algorithm, cluster W, and many
No, we use BAM-SAM format, which is BAM is binary alignment and mapping. I'll talk about it briefly. And for variant calling, we use SAM tools or we